The lesson for patterning in algebra is called Backyard DIY. And just to give you a little idea of what's happening is students are in a scenario where they have to build square patios, a square patio for their backyard. And so the first part of the lesson asks them to use color tiles to build square patios, starting with the smallest they can build up to one that is 10 by 10. And as they build these different patios, they collect this data here. And so what I like about this lesson is that it offers students a chance to transition from a simpler way of conceiving patterns to a more sophisticated way. A lot of students think of patterns in terms of adding or subtracting a constant, or multiplying or dividing by a constant. So in other words, they might take a pattern like this one and say I start at 1 and I add 2 each time to get the number. They're always going down the columns. I try to get my students to look across from, in this case, the term number here to its corresponding value. So what do I do to 1 to get 1? What do I do to 2 to get 3? And the actions need to be the same. So this is using the term number to describe a general term, and in this case you obviously multiply the term number by 2 and subtract 1 to get the corresponding number over here, and that is the basis for the algebraic expression below. So this lesson offers students several opportunities to work through that process and develop a more sophisticated way of looking at patterns. They do that with the square patios, and in the second section of the lesson they are again working in their backyard, making renovations, and they need to build a staircase from one level of the backyard to the other. And again, they use color tiles to represent the sides of the railway ties they are using for the staircases. And this scenario generates different patterns that they look at and interpret, and again try to look at in terms, not so much in terms of starting at 4, for example, and adding 4 each time, but taking the number of steps in the staircase and multiplying by 4 to get the perimeter of the staircase, and ending up with the algebraic expression 4n. So that's one thing I really like about this particular lesson. It provides students with the opportunity to do that. Now, in this column right here, we have a set of numbers which are called triangular numbers. And we can see that we're basically making larger and larger triangles here. Okay, this lesson is also a very good opportunity for students to think deeply about sets of numbers of this type. And I'll show you what I mean. So we have our triangular numbers here, 1, 3, 6, 10, 15, 21, and so on, and you saw those right here. But when you sit down and analyze these and look at what is going on, I mean, obviously there is the algebraic expression n times n plus 1 divided by 2. That will give you the value in any given the number of railroad ties for any given number of steps in the staircase. But if we take a look at what's going on here, we add 2 to get from 1 to 3, then we add 3 to get from 3 to 6, and I'm adding 2, 3, 4, 5, 6. The number that I add changes by positive 1 each step. Now, on its own, this might not be the biggest revelation until we take a look at a similar chart for square numbers. And if students analyze the pattern this way, they're going to see something very, very interesting that is kind of hiding. And it's surprising, it's unexpected, and it's aesthetically pleasing to see that we have a similar pattern going on here with square numbers. We're not starting by adding 2, we're starting by adding 3, and the numbers that we add to go from square number to square number increase not by 1, but by 2. Now, at this point, these are numbers that the students will have encountered in the lesson, but as a tangent to this lesson, as a point of interest, you might ask students, well, if there were a third um, category, what would we call it? What would the title be? And what would the numbers look like? Can we predict this? Well, if we have triangles here and we have square numbers here, then we might actually have something called pentagonal numbers. And in this image, you can see visually how triangular numbers increase, how square numbers increase, and logically, pentagonal numbers increase the same way. Now, at this point, students might say, well, okay, well, we started at 1, pentagonal numbers are going to start at 1. Instead of adding 2 or adding 3, we're going to add 4. And 1 plus 4 is going to give us 5. But instead of increasing by 1s here or 2s here, we're actually going to be increasing by 3s. So 1 plus 4 is 5, and now I'm going to increase by 3, so that would be adding 7, and I'll be adding 10, and this is what we end up with. So it's a very surprising, in a good way, a very surprising and aesthetically pleasing discovery that pentagonal numbers, although the numbers are wildly different from square numbers and triangular numbers, the way in which they are built is surprisingly similar in terms of where you're starting to increase and the increments by which the increases themselves increase. And so this investigation can be fairly rich and ongoing, because after pentagonal numbers you can go into hexagonal numbers and the rest of them, and it's quite an interesting discovery for students to have. So we've actually gone maybe a little bit away from patterning and algebra and more into number sense and numeration, but that's completely appropriate, seeing as it's kind of nice to break down the walls between strands of mathematics.